Hey guys, it's Miss Johnson, and I'm here to bring you our notes for the second part of section 6.3. We are still talking about binomial distributions, and today we're going to talk about how to describe a binomial distribution. So when we are describing a binomial distribution, I want you to think back to chapter 2 when we would describe normal distributions or other graphs and charts that we would be looking at. And the same kind of concept is going to be used here. So we're going to talk about the shape, the center, and the spread, or in other words, variability of the distribution. So in this case below, it says the table shows the possible values and corresponding probabilities for X equaling the number of children with type O blood from the previous examples. This is a binomial random variable with n equaling 5 and p equaling 0.25. So remember, this was that family that was going to have 5 children, and each child independently had a 0.25 chance of having type O blood when they were born. So you have a possibility of 0, 1, 2, 3, 4, or 5 children with type O blood. So the probability distribution looks like that purple graph right there. And when we look at that graph, we can clearly see that the graph is skewed to the right. So the binomial distribution with n equaling 5 and p equaling 0.25 is skewed to the right. That's how I would describe this distribution right here. A couple of key elements. You have to state that it's binomial. You have to state what the n is. You have to state what the p is for each individual trial. And then you talk about what it looks like. Okay, so those 3 pieces are going to be important when you're writing these things out if this were the AP exam. So if I look at these two, a couple more examples. The first one on the left, it says the binomial distribution with n equaling 5 and p equaling 0.51, which you can see they give to you, is roughly symmetric. It looks approximately normal even, but yeah, I would definitely say that it's symmetric with one peak in the middle. You know, it's at across 2 different areas, but it's not like it peaks, goes down, and then comes back up again. Over here on the right, now you've got n equaling 5 and p equaling 0.8. So the binomial distribution with n equaling 5 and p equaling 0.8 is skewed to the left. And in case you forgot, that skew follows the tail. Okay, skew follows the tail. So that's just a note from back in chapter 2. So wherever the tail goes, that's where the skew is. So when we're describing it, it says if a count X of successes has a binomial distribution with number of trials n and the probability of p, the expected value, here's some formulas for you that we're going to look at today. The expected value of these is n times p. That's a really simple formula to do. And then the standard deviation is the square root of n times p times 1 minus p. So those 2 formulas right there are formulas that you will use to find the mean and the standard deviation only for binomial distributions, okay? Only for binomial distributions. And on the formula chart, the formula sheet that you get for the AP exam, these 2 things are on there, okay? So you will see those 2 formulas on your formula sheet, but these equations are ones that you will use to find the mean and the standard deviation for a binomial distribution. So, yep, this is only for binomial. That's the caution there. We don't use these for any other thing. You're going to learn about geometric distributions in this section as well. That's going to be our next lesson. And those have a totally different formula, and they have a different way, you know, what makes them geometric is different than what makes something binomial. So remember, binomial, if you forgot from the first lesson, binomial is binary, meaning there's a success and a failure. You have a fixed number of trials. That's important. Fixed number of trials, meaning you know you're going to have 5 kids, or you know you're going to flip the coin 10 times. And then each trial is independent from the next. All right, so let's talk about those let's practice with those formulas. It says, assume that each of the 21 students in Mr. Hogarth's AP statistics class who did the bottled water versus tap water activity was just guessing. So there's a third of a chance of each student identifying the cup containing bottled water correctly. Let X equal the number of students who make a correct identification. So this must have been an example where students were trying to determine if they could figure out which cup had bottled water in it. Is there a taste difference between bottled water and tap water? So it sounds like there were 3 cups and they had to pick one that had the bottled water in it. So it says let X equal the number of students who make a correct identification. At the right is a histogram of the probability distribution of X. So you see the probability distribution, or you see a histogram of the probability distribution. We don't have the actual table, but that's okay. We have a histogram of it, so that's good. The first thing says calculate and interpret, keyword there, the mean of X. So mean of a binomial distribution is just simply n times p. So in this case, we would make that 21 times a third, which is 7. But now here's the key word where we have to interpret that. And when we interpret that, we need to say something, we need to address the fact that they were guessing. So if all students in Mr. Hogarth's class Mr. Hogarth's class were just guessing, and repeated the activity many times, that's important. The average number of students who guessed correctly would be about 7. The average or mean, whatever you want to say, the mean number of students who guessed correctly. About 7. Okay, so a couple of key pieces to this interpretation. You know, this is where the real meat of the answer comes into play. This is going to be important for your AP exam on how you write these things out. So we address that they're guessing because that means that every probability is the same. We're assuming that everybody's going in with the same knowledge, or in other words, without having any knowledge. They're just going in and guessing. The repeating it many times. Okay, remember that the variability you can't make predictions in the short run. You can make predictions in the long run, but you can't make predictions in the short run. So we want to repeat the activity many times, and then you put it in context. Mean number of students who guessed correctly would be about 7, and then give your answer there. All right, so now let's talk about the standard deviation. So we're looking at the same example, same histogram. We've got the same probabilities and the same number of students, but this time we're looking at the standard deviation. So let's talk about standard deviation. Your standard deviation of X is going to equal the square root of, you need n times p times 1 minus p. So we'll talk about what that is. That 1 minus p value is like the probability of failure. So if p is equal to 1/3, that means that 1 minus p is equal to 1 minus 1/3, or in other words, 2/3. So basically what they're saying is 1/3 of the students are going to guess correctly, but 2/3 of the students are going to guess incorrectly. Okay. So in this case, my formula would look like 21 times 1/3 times 2/3, and take the square root of that whole thing. So I'm going to pause a second and plug that into my calculator. Square root of 21 times, I always put my fractions in parentheses to make sure that my calculator knows that it's a fraction and it needs to stay together. So I have the square root of 21 times 1/3 times 2/3, and I end up with 2.16 there. So the standard deviation of X is equal to 2.16. So if I'm going to interpret that, that means that if all students in Mr. Hogarth's class were guessing, or it starts off pretty much the same, because again, the interpretation is the key here. If all students, I'm going to try and write small because I took up a little more space, in Mr. Hogarth's class were guessing, and repeated the activity many times. The number of students who guessed correctly would typically vary. Now we're talking about the variability. The number of students who guessed correctly would typically vary by about 2.16, but you're not finished, with a mean of 7. You got to state that mean. When you're anytime you're addressing the standard deviation, you have to state the mean. So there's all the pieces that you need. They're guessing, that makes each probability the same. They repeat the activity. You put it in context with the students who guessed correctly. You say typically vary, that's addressing standard deviation. And so then you say what the standard deviation is, and then you state the mean. Okay, so almost all real-world sampling, such as taking an SRS from a population of interest, is done without replacement. So what that does is it makes things a little bit different, okay? So when especially because we're usually dealing with live subjects, like a lot of times we're dealing with people, so you're going to pick one person, but then you can't pick that person again. Even if you're doing it with like animals or something like that, you're going to pick something, but then you can't pick that same item again. So sampling without replacement leads to a violation of the independent condition in a binomial setting. So that creates a problem for us. The fact that we are not replacing the item makes our binomial distribution, makes our binomial setting a little bit flawed. It puts a flaw in the setting. So what we have to determine is, are we pulling from a large enough population? We have to look at our sample size compared to our population and decide, is our population large enough where the the sample that we're pulling is not going to make that much difference in the probability because our population is large enough. So that's kind of what they're getting at in this second point. It says, but when the population is much larger than the sample, the count of successes in an SRS of size n has an approximately binomial distribution. So, we know it's not going to be perfect because we're not putting the item back. But as long as our population is large enough, we can still use our binomial setting properties and calculations because the probabilities are not going to change too much with a large enough population. So here's what you have to check. We call this the 10% condition. It says when taking a random sample of size n from a population of capital N, we can use the binomial distribution model to count the number of successes in the sample as long as this is true. We need our sample to be less than 10% of the population. That's what's happening here. So we have to check that 10% condition. We call that the 10% condition. As long as our sample is less than 10% of our population, then we're okay. Then we're allowed to use binomial calculations. Since we're allowed to use binomial calculations, we can proceed with whatever we're trying to figure out or solve. If the sample size is not less than 10% of the population, if our population is really small, then we have to back up a little bit and we can't use those binomial calculations, okay? So this is what you're going to be determining in all of your binomial settings when you start calculating things and stuff like that. You have to state, is your sample size less than 10% of your population? All right, so let's look at a question here. It says, in a survey of 500 U.S. teenagers from age 14 to 18, subjects were asked a variety of questions about personal finance. One question asked was whether teens had a debit card. Suppose that exactly 12% of teens aged 14 to 18 have debit cards. Let X equal the number of teens in a random sample of 500 who have a debit card. So explain why X can be modeled by a binomial distribution even though the sample was selected without replacement. So basically what we have to determine here is, does it fit the bins? Is it a yes or a no? Is it, success or failure? Is there a fixed number of trials? Is there an independent p-value? And then we also now need to check that 10% condition, okay? So for part A, we know that there is success or failure. Failure, and that's a check because it's either debit card or none. So you either have a debit card or you're not, or you don't. The next thing is, do we have an independent? Yes, because one teenager does not affect the next. So then is there a fixed number? Yes, that's a check because we're pulling 500. So that's our sample size. And then we need to check that 10% condition. So the 10% condition would say is 500. So 10%. Okay. Our 10% condition, we have to ask ourselves, is 500 teenagers less than 10% of all U.S. teens? And I would say very quickly, yes. Even if you think about just Farmington High School is 2,500 teens, you put two high schools together, you've got 5,000 teens. That's less than 10%. And we're talking about all U.S. teens. That's going to be millions of people, okay? So 500 teens is certainly less than 10% of all U.S. teens. So we're good there. So my 10% condition checks out. So I'm allowed to use a binomial distribution because of all of those things. And then let's take a look at B. It says use the binomial distribution to estimate the probability that 50 or fewer teens in the sample have debit cards. So now we're going to go back to that binom CDF. So X is approximately binomial. X is our variable there. With N equaling 500 and P equaling 0.12. That comes from that probability that they gave us. So then the probability of X being less than or equal to 50 is going to equal my binom CDF of trials being 500. I always run out of room, you guys. Sorry. Probability being 0.12 and X being 50. And that is going to equal, so in your calculator, in case you forgot how to do this from the first video, you're going to go to second distribution. Binom CDF is down near the bottom. It's not on the main screen, so you got to scroll a little bit. For me, it's option B. So binom CDF, remember it's cumulative. My trials are 500. My p-value is 0.12. And then my x value is 50 because remember, I'm always measuring to the left. So I want less than or equal to 50, which means I'm going to go 50 and below. So 0.093-ish. 0.093 for a probability there. Okay, so now we're going to get into how we can determine if a binomial distribution is approximately normal or not. So one thing to take note of is as our n increases, just like back in chapter 2 and also in chapter, I think, 4 and 5, we talked about how the more trials you have, the more closer to a normal distribution you can get. So that's true with binomial settings as well. So if you take a look at these graphs, this is a binomial setting where p is equal to 0.8 and my n is equal to 10. So it looks approximately normal. It's okay. When I increase my n to 20, check out this histogram. Look at how much more normal it even looks. And then even further than that, when I increase my n to 50, now you can really see that there's that normal curve there. So as the number of observations becomes larger, the binomial distribution gets closer and closer to normal. So that's going to help us when we're doing some of these calculations. We like distributions that are normal. It helps us. So one way that we can work, or we can determine if something is normal or not, because again, as long as we can justify that our distribution is fitting a certain parameter, then that opens the door to all sorts of calculations and analysis we can do. So the other thing that we have to check, we talked about the 10% condition, saying that a distribution, the sample size is less than 10% of the population. That allows us to use that distribution even though we're not replacing an item or replacing a subject. The other one that we're going to check is the large counts condition. So what the large counts condition says that if your expected number of successes and failures are both at least 10, then you can call your distribution normal. So the way you calculate that is you find the expected number of successes. Remember that expected number or mean? Okay, that mean was n times p. So if I take n times p and it's greater than or equal to 10, then I know that my distribution is normal. Well, I have to do both, sorry, and the expected number of failures. So if I do the expected number of successes and the expected number of failures, and they're both greater than or equal to 10, then I can call my distribution normal. And that opens the door to a whole lot of analysis that we can do with these. Now you're talking about probability, you're talking about a valid standard deviation, you're talking about normal CDF. There's a whole lot of things that you can do when you determine that your distribution is normal enough for you to work with. Okay, this is called the large counts condition. So those are those two conditions that we're going to use when we're talking about a binomial distribution, the 10% condition and the large counts condition. So let's go back to this 500 teenagers. It says, justify, I'm using the same example, 500 teenagers, 14 to 18, debit card or not, P is 12%, all of that stuff is the same. Justify why X can be approximated by a normal distribution. So in part A, if I know that N times P is greater than or equal to 10 and N times 1 minus P is also greater than or equal to 10, then I can say that it is normal. So in this case, I have 500 times 0.12, and we're checking, is it greater than or equal to 10? That's our question. So when I type that into my calculator, 500 times 0.12 was 60. 60 is greater than or equal to 10. So check. How about over here? Over here for the failures, do we have at least 10 failures? So we have at least 10 successes. We expect there to be 60 successes. So then for our failures, we do 500 times 1 minus 0.12, or in other words, 0.88. Is that going to be greater than or equal to 10? Well, yeah, of course it is, because 0.88 is a lot bigger than 0.12, but we'll just go ahead and calculate it anyway. That's going to be 440. So that was our question here. We get 440. So that means we expect to get 440 failures, or in other words, students who don't have a debit card. So that's good for us. We expect about approximately 60 U.S. teenagers to have a debit card, and we expect approximately 440 teenagers to not have a debit card. Both of those things are greater than or equal to 10. So then yes, we can call this normal. Remember that we always want to use the word approximately because you don't know if it's exactly normal, and chances are it's probably not exactly normal, but it's normal enough. This is our justification by saying it's normal enough for us to use normal calculations. So then it says use a normal distribution to estimate the probability that 50 or fewer. So now we're going to do the same calculation that we just did in the last example, but we're going to use normal CDF instead. So our normal CDF is going to look like we've got a mean. We need a mean. And we just did the mean up here. N times P, 500 times 0.2, which gave us 60. So we know our mean is 60. Now we need the standard deviation. That standard deviation is going to be the square root of the 500 times 0.12 times 1 minus 0.12. And that just comes from those equations that we know for binomial mean and standard deviation. So I'm going to type all that into my calculator. Square root of 500 times 0.12 times 1 minus 0.12. And I get 7.27 there approximately. Okay, so there's my mean, there's my standard deviation. Now I'm using normal to calculate this. So normal CDF is going to be a mean, or sorry, you have to do lower and upper first. So lower bound, we're going 50 and below. So I'm just going to say that my lower bound is like negative 1,000. Or you could do that negative infinity. I think we would do negative infinity sometimes. So negative 1,000. And then we would have an upper bound of 50. And then we have the mean of 60, and we have the standard deviation of 7.27. Remember that when you write this out for the AP exam, you have to identify what these characteristics are. You have to say what those values are. So now go back to your calculator, go to second distribution. Normal CDF is option 2. So I already have negative infinity in for my lower bound, so I'll do my upper bound of 50. My mean is 60, and my standard deviation is 7.27. And I get 0.084. So my probability here, that x is less than or equal to 50 is equal to 0.084. So you can see that it's a little bit different than the probability we had using binomial distribution. When we used that, when we did binomial distribution, we had a probability of 0.093. So they are a little bit different. They're a little bit different calculations, and it just depends on what you are looking at. But both are justified. Remember, we proved the 10% condition, we proved the large counts condition. We can use either one. Either one will work for us. So again, it just depends on how you're looking at things, what calculations you're asked for, how you're asked to analyze it. And in this case, they asked for a normal distribution. All right, so hopefully that gives you a little bit of a picture of how to describe a binomial distribution, talking about shape, talking about center, talking about spread, talking about how it can relate to normal distribution, and those two conditions, the 10% condition and the large counts condition. So thanks for tuning in, and I will catch you next time.